nice to see a swarm of yellow jacket students out there, and hopefully with this swarm of people we'll be able to build up our intelligence base. That's what we're going to talk about today. Dr. Matthew Allen Baueregard is going to discuss with us some matters of swarm intelligence and agent-based modeling in engineering and biology. And Dr. Baueregard has his PhD from the University of Arizona and a postdoc from there as well. He's also associated with Baylor in their research, and he's an adjunct professor at Baylor as well. He's been a professor of math speaking at Austin University, and we've had other speakers from there recently. And just down the road, over there in Nacogdoches. But next time you're driving through that way on your way to Houston or something, you can stop in and visit Dr. Baueregard in Nacogdoches. Show you around, check out the math department, stuff like that. They got beautiful trees on their campus there.
You can go tree climbing.
You can go tree climbing, yeah. Big forest. We had remember our forest last week. He's from speaking of Boston as well. All right. So after the seminar, we'll have lunch with Dr. Baueregard over in the corner cafe over there. And if you want to join us to talk more about, all this artificial intelligence and nanobots and things of that sort, you can come and join us there at lunch. Until then, let's welcome Dr. Baueregard.
I've always thought that when I enter class, that's the way I should enter. When I enter class, it should just be like the roaring applause, like an athlete coming into the football stadium, and you put like a ticker tape or something, and then you get done, I get the same type of round of applause, but it doesn't happen that way. It doesn't happen that way. Well, I'm excited to be here and with you all today as well. We're not going to talk too much about bees. That would be sweet. But unfortunately we're not. But this is going to be some work that I've done collectively with a few different undergraduates over the last 5 years or so. Okay. And the original work was funded through DARPA. Now DARPA is Division of Armed Research and Programs and Activities for the United States. And it was pioneered through a friend of mine who's at Baylor in their electrical engineering department. His name is Robert Marks II. He's also a devout Christian, and always when they have one of these like most influential scientists of the world, Bob's on there. So he's one of those eccentric fellows that just, if you can just get him to be focused on a problem, he can get something done really good. But and I got interested in this mainly because I'm interested in applied mathematics, and I look at mathematics as a gigantic toolbox to be able to explain natural phenomena. And I look out into the biological world, and I see these unbelievable smart bugs doing unbelievable things. And your class example is like creating a honeybee hive. Like, how is this relatively unsophisticated bug, it's not even sentient like us, and how can it just be designed so well to do these incredible tasks and make a honeybee hive? Like, if I had to take paper mache and do this, I couldn't do it. So I want to know what's going on in the mechanism of the individual bees to be able to create such a thing. What set of rules is it following that you get this macroscopic behavior occur? Okay, that's what I'm kind of interested in. And so we have lots of different examples of swarms that you're probably familiar with. And so let me get over here. I'll give an example of this. You get, schools of fish, and to tell me like why you would think some schools of fish would swarm together. What would be some reasons?
Look larger.
Like look larger, so maybe for safety. Okay. If I'm the bully in the room, and since most of you are STEM people, okay, you want to stay together, and I might be less likely that I'm going to come after you. Okay, you can team up, or you can team up against me, what have you. What's another reason? So, kind of do it there. I can't remember the name of if anyone's a biologist here, maybe they can tell me that. I can't remember the name of the ants, but they're found in the Amazon. If you don't know where an insect is, you just say it's from the Amazon, then you're right. But these are from the Amazon. And that's a swarm. They're doing So what are they trying to do here? Working together to accomplish some tasks. So in this case, these are ants, they never touch the ground. They always stay in the trees. They live in the trees, okay? And they go from tree to tree by actually making a bridge and climbing on each other's backs, okay? Ants are unbelievably fascinating to look at. Just a regular type of ants, not red ants. Those are not fascinating to look at. They're only fascinating to kill. Okay. When eventually, I have a couple questions when I finally come face to face with Jesus, and one is going to be what's the purpose of poison ivy? Okay, and the second is going to be what's the purpose of red ants? I'm fairly convinced he's going to say, in the garden, poison ivy was a delicacy. And I'm going to say, yeah, that would make sense. And red ants were actually helpers that brought the delicacy to you. I'm fairly convinced that's what he's going to say. But so, how do they know when to make that bridge? How do they know that I'm supposed to be the person you have to walk up? What set of rules do they follow that guarantees this behavior is going to happen? Okay. And of course, classic example, swarms of birds. Okay. And what have you. So this is a good example of, say, dweebs and bullies. So I like to say, you have the bully, the hawk, and all the dweebs, the birds. Okay. And something that's interesting with all three of these situations is, well, especially these two, is that there's a characteristic scale kind of in between. They keep a distance between them. Okay, like if you and I all got up together and we started walking outside, there would be kind of a distance that we would keep. Like, for instance, if you and I were walking down the hallway, we wouldn't be like this close. That's way too close. But we wouldn't be like this far away because no one would know we were walking together. So they kind of there's this social attraction and social repulsive force. How do they know to do that in that particular swarm of birds? Like, how do they know that that's the optimum distance? I find this kind of fascinating. But again, like, these birds that are very far away can't see that bird. Only these ones can. So how are they communicating? And yet, when I look at this from a macroscopic perspective, it looks like it's just one giant, animal moving. I mean, it's breathtaking to watch. You ever see them, at an evening and just sit and memorize? Or am I the only one with that? Like, sit and just memorize looking at swarms of birds. It's just how they move. It's so fluid. Okay. And of course, you have your honeybees as well. It can go on lots of time, long time for honeybees. Hey, this is kind of cool. I learned this past week with honeybees, so I'll share this with you. So you get the classic hexagonal structure of a honeybee, the hive, okay? And they put a cap on that, and you would think it's like a flat hexagonal shape, but they don't. It's it bulges out a little bit, and apparently the bees know Calc 1, okay? Because they figured out the shape that would maximize the volume of a hexagonal tube. Isn't that kind of cool? But, it took a few hundred years of people looking at this problem. They found out actually there is a little bit better way that they can orient their hive that would actually make it increase the volume, but it's like by 0.001%. Okay? Isn't that interesting? But this is the easiest one and to get to. So it's incredible that they did that. They weren't taught that. One of my favorite books is Charlotte's Web. Okay? And there's this great classic scene in Charlotte's Web. It's the mother's really concerned about her daughter because her daughter's like, she spent all this time in the farm. She's not spending any time with her friends. She's now saying that this pig talks to her. And so she goes to the psychologist, goes to her doctor, and says, you got to help me. Like, she thinks, like, these animals are talking to her. And he's completely attached. She's spending all her time on the farm. And now they're saying that this spider down there made some web, and it had words in it that said some pig. This is preposterous. And I love it. The doctor says to her, goes, you're missing the point. He goes, it's amazing that the spider makes that web in the first place. It automatically is born with this complete knowledge to make this web, to spin this web. That's the miracle within itself. So the doctor wasn't impressed at all about the sun pig. We were. But, okay, well, let me give you, a couple things that I want to show. One is that, I would say I'm an applied mathematician. I want to develop mathematical models for a collection of rules that I think that a certain type of set of swarms may be following. I also want to look at a certain set of swarms and maybe figure out what set of rules that they're following. So there's this forward engineering problem, there's also this reverse engineering problem. And then I want to make simulations to be able to look at that. And that's, I would say, in the lab testing. Okay, and there's lots of videos in here that are made by students that have worked on this at this site. Let me just go, yes, and here, and it's coming up. Let me see. What screen does it come up? Let me go over. Let me see. I'll go here, and then I'll go like this. Okay, this website right here, why can't I get it to show it over there?
Drag it out.
Do I have to drag it? Oh, because it's two monitors. Is that what's happening? So where's the other monitor? Oh, there it is. Oh, okay. Thank you. Okay. Well, it's gonna be hard for now. I'm looking here. Okay. These are some videos that you can just kind of play with and looking at different swarms. And it's hard for me to look at now. Let me see. And well, I'll just go back actually over here. Instead, I'm going to look at. So now I got to get my cursor, and I'm going to enable that in. Hold on. Hold your taters. Hold your taters. Slideshow from current slide. Let me see. There we go. So instead, what I'm going to show you. Let me see this video go. Oh, it didn't. There we go. It's not going. Oh. Well, I'm going to do something else instead. I don't know why that's not showing there. So we'll go up here. I just have a hard time seeing it. And that's unfortunate. Do I have this thing? There we go. Let me go DARPA. I'm just going to find the video itself. I want to show you. I typed it in right. Okay. Well, what I'm going to show you here is, this is a challenge that came out by DARPA. It pitted together 3 different academies, West Point, the Coast Guard, and the Air Force, to go from what's called zero to swarm in a capstone engineering project. So they wanted to do zero to swarm in an academic year. And some of the code that they used to kind of seed this is you're going to actually see that developed over here. I'm not sure why it's not going. Okay. All right, I'm going to skip that then. So, sorry. It's a bummer. Okay. So let me go from current slide. So I'm going to skip those videos. Unfortunately, that's a bummer. And so, okay. So I want to go through 3 different simple scenarios. These are called ICO systems. These are single agent swarms. Okay. And what I want to do is before I get too complicated in trying to understand, say, bees or birds or what have you, I want to understand if I just write down some very, very simple rules that a single agent would follow, if I can write down a mathematical model for that. and then be able to make some predictions of what might happen. Okay, so the first one, I'm just going to describe the set of rules, and we're going to walk through it here, and then we're going to kind of make some predictions about what will happen. Okay, so the first one I call is a creepy follower. Okay, and this is just follow the leader. So simple rules. Rule number one, okay, is that no agent knows other people's rules. Okay, you can think of that means if I'm making a drone, the onboard computing system there cannot speak to another drone. Okay, or they just do not know their code. They're independent agents within itself. Okay. Rule number two is that it's going to select another agent in the room. Okay, and it's going to try to maintain a minimum distance between there. So here, 3 feet could be 6 feet or what have you. So think about if we did in this entire room. Everyone picked one person. Everyone picked one person. And we have probably about 80 people or so in here. Everyone picks one person. I want you to maintain a 3-foot distance. So 6 feet. Okay? And then we start that process. You're not allowed to run into each other and what have you. We'd like to know what would happen. Well, it would be chaos at first. Right? It'd just look completely crazy. But what do you think would happen? What do you think? They're going to end up circling around? I think that's a good conjecture. Now, why do you think that?
Well, everybody will be moving, so that person will be maintaining their distance from another person, and that person will be moving, and that person will be moving, and so they'll all be moving together.
Yeah.
To maintain that distance.
Yeah. Okay. Now, go on.
Well, like, theoretically, once, like, eventually everyone will just stop. It'll still be like a giant blob, but everyone will stop moving because they'll reach that, like, perfect distance between them and then the person who's 3 feet.
Everyone hear what he said? That it could. These are conjectures. Conjectures are they're kind of well-educated guesses. Okay, unfounded claims. But what's your name?
Robert?
So Robert's saying it could stop. Now, tell me your name, sir.
Curtis.
And so now Curtis, okay, I'll say Dr. C over here is saying, look, it's going to keep moving. So could we get a situation that maybe they stop circling? Or maybe we can get a situation they always keep moving. I don't know. So let's say we have 3 agents. So can I use you 3? Okay, now come with me. Okay. So let's just run this simulation right here. Okay, so each of you pick someone. Okay, don't tell who you're picking. Okay. 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 And just move slowly so you can get about, let's say, 3 feet from each other. 3 feet. Or as I say to my kids, it's a Liam size. This big. So they stop. So you must have him. Who do you have? Okay. Who do you have? Okay. And who do you have? Okay. So they stopped. Okay. Now, can I have you as well? Okay. Would you pick him instead? And you just pick someone. So you can definitely get static configurations. Okay? You can definitely get static configurations. Now, so here's the thing. Can we ever get them to be constantly moving? And that would be an interesting question. Will they always move, or will they always end up in static configuration? You guys can sit down. Okay? So that is something I want to be able to either show experimentally, and if I see that happen experimentally, if I code this, I want to then see that mathematically. This is a limit. The limit as time goes to infinity. Do I end up with a static configuration? The velocity ends up being 0 for every single agent. Okay, you can see kind of the undergirding physics and mathematics. Now, let me see if this will work over here. Just to show you, I want to look at a large simulation. This is with 1,000 agents. Okay, and I'll see if this goes. Let me see. Let me scroll over here. Okay, can I get? Oh, I can't because it's all in Python, I think. That's why. Okay. What's that?
Did you use Chrome?
I don't know. I have a hard time with the other screens. Let me see. I go there, go Chrome. Let me see. So we're gonna play here. Let me see. No, I need Flash to do that. Oh, that's a bummer. That's a bummer. That's a bummer. That's a bummer. It's a pretty simulation you're missing. Okay. I should do it this way. Take out your phone. Why did I take out this before? Okay. Neoswarm.com. So go to neoswarm.com, neoswarm.com. Okay, it's not going to be optimized for your mobile device. Okay. And click on Ecosystem, the second one. If you scroll down,
Click on what?
Bummer. Again. Doesn't look like my trick is going to help. Oh, that just stinks. It's really, really pretty. Okay. More information. Yeah, so let's go to number 4, which is called the follower. Okay. And click on more information. I'll see if I can get that over here as well. You know, we're kind of needing to improvise a little bit here. So I'll click in here. This will at least show snapshots of the picture. So I don't think this is, I think how many agents is this one? This is 1,000 agents, but it only shows just a small snapshot of the field. And again, it's just doing some sort of follower. Okay, and what I'm doing, I'm keeping the contrails, so this kind of shows the overall movement. So, and they eventually fade off, and just kind of like a contrail for a comet or what have you. But you can start seeing they're getting a circular pattern. Exactly what Dr. C said. Okay, I got some sort of circular pattern. Now, there is a boundary condition that's being imposed on these agents. This, if you think about it, this is the entire world. I'm allowing it to be a closed Earth. So I'm allowing, when it gets over here, it's wrapped around over here. That's called a periodic boundary condition. So I allow it to go off here and enter over here. Just like if I went due east, I'd end up due west if I went long enough. Okay. If we did a simulation here, think about this. We're like an island. We can't get out. If you hit that wall, you stop. So I don't have that. That simulation is not showing. But you get these beautiful type of circular orbits. And the interesting thing is that if we run a bunch of simulations, I'll show the kind of the end result. Okay. They eventually all, like this one collapse, they kind of collapse down to a little static pocket. Okay. And eventually this little pocket right there will collapse down just static. So experimentally we're seeing lots of circular motion, but eventually they kind of collapse down to a stationary point. Okay. Okay, so let's deal with a different example. Okay, I'm going to up the ante a little bit. I call this the coward. Okay, call this the coward. Okay, here are my rules. Okay, still, they're all private. I'm going to select 2 people. So let me get 2 other volunteers. Can I get you 2? And I'm gonna have you as well. Okay, what's your name? Richard? Quinn? Cameron. So Richard, Quinn, and Cameron. So Richard, you're gonna choose Quinn and Cameron. And your goal, you think that Cameron is gonna beat you up. Okay, you can do it. Okay, so, but you think he can protect you. I mean, look how tall he is. So you want to keep him in the middle, your midpoint of the line segment that you have. So you would kind of almost be right here. Okay. Now, you also need to pick two people, and you're going to, say, you also think Quinn is going to beat you up. I'm not Quinn, sorry. Cameron. So, Quinn, you also think Cameron's going to beat you up. So, you want to make him your protector. Okay? And that's what I have right here. So, move the second person selected is equidistant from you, and the first person selected. That's what I mean by that. Okay? So, you're acting as coward. So, let's kind of get over in here. Okay? So, now let's try to run this simulation. Okay, very slowly. Who you selected? Who you selected? Okay, so who was your first person you selected? Okay, so you selected him, so you're going to put Quinn right in the middle. Okay, now, and you have, who you selected? Here, these are you. And now is your first one. Okay, that's your first, Cameron was your first one? So if Cameron was your first one, you're going to be rotating over here to have him be your midpoint. Okay, so let's see if you guys could just walk slowly as you kind of, who are your two?
He's protecting.
Okay, so right now you're in first position, but you're not. And Cameron, did you have Quinn was the person?
He is the guy.
Okay, so you're in a good position right now. You're the one that's going to have to move. Okay, so start moving slowly. That's going to make everyone else move as well. Now, Quinn, you're going to have to be more aggressive and move around. All right. Now notice here, are they all obeying the rules?
Yes.
No, they're not, right? There's actually some social rules that they're obeying that forces them to disobey the rules that they're being programmed to do. Okay, now think about it. A computer programmer doesn't have the luxury. A computer program, you say, if I wanted to evaluate x squared at 2, and my program is square the number, I give it a number, it can't say, I want to take the sign of that number. It doesn't have that luxury. It just squares a number. So, you kind of see, there's awesome social dynamics. All right. Here, you guys sit back down. So, suppose I took all of you guys with this, okay? All of you guys want to put yourself right in the middle, or say you're gonna put your second person you selected right between you and the first person. So all of you play the coward. What would happen? What happens? Well, let's actually, since I can't look at a simulation, I can at least go back and look at Neoswarm. So let me go back over here, and let me, I'm sorry, let me go over here. Okay, let me go to the cowards, and I'm going to go to more information. Okay, and you can do this on your phone as well. Okay, so this is a case, I have 1,000 agents. Okay, and I put 1,000 agents all really close in proximity to each other. Okay, they're like a 0.001 distance from each other. And this is just shows snapshots of what's going to happen. So again, each agent has selected 2 other agents. And it's trying to strategically keep its second agent at the midpoint of the line segment between agent 1 and itself. Okay? So it's kind of being a coward. Okay? And as I go through, and you kind of see it start moving, and then now you can start seeing all the agents. Okay? Keep on seeing. Keep on seeing. On there. So what happened? What's that? Now here, Here I actually have that this is, it goes on to infinity. Okay, I don't have a periodic boundary. I remember, don't have a periodic boundary. But, like, how many agents do I see here? I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, like color lines at 16, 17, 18, versus 1,000 or so. But think of what happened if you had to explain this. I mean, what does that look like? It looks like an explosion, doesn't it? Especially when I leave the contrails on. It looks like something you see at July 4th. Okay? So, I'll tell you this. Every initial condition that I choose, every single initial condition I choose, if I choose enough agents, okay, let's say 10 or more agents, okay, every single initial condition I choose, it ends up having the same dynamic, exploding. So, if that happens in every single experiment, that makes me make a conjecture. Then maybe this is true always. And if it is, maybe if I get a mathematical model, maybe I can siphon out of that mathematical model if it has that same property. Okay. Well, let's look at another situation here. So let me go back over here. Oh, I skipped one. I thought I did. Thought they were out of order. I got the peacemaker. So peacemaker a little bit easier to describe. Peacemaker is this. You select the two agents. You just put yourself right in between. Okay. So you look at two people and you're like, oh my goodness, I really think those two people are going to fight. I better get in the middle. Okay. So that's the peacemaker. And so if we did that everywhere in the room, okay. You know, let me take like 5 people. I mean, you 5. Come up. Okay. I want you, don't tell me who you chose. You're going to choose 2 people. Okay. You're going to choose 2 people and just put yourself right in the middle. Okay. Spread out a little bit. Okay. Spread out. Okay. Come over here. Okay. You walk pretty slow. Walk slower. I don't want to fall down. Okay. Here, let's stop. Okay. Let's have you spread out more. Okay. Someone go up the stairs here. Someone go over there. Someone go over where Kurt says. Someone go by me. Choose a different 2 people, but again, you're putting yourself right in the middle. Okay. Different 2 people, and go. Okay, cool. Now, we did a couple different initial conditions there. What happened in both situations? What's that?
They mix together.
They mixed together, okay. They got
Together.
compact. Okay. If I add some more people in the mix, I mean, let me add, you three. Okay. Add you three. Okay, gotcha. You just pick 2 people. You just pick 2 people. Okay. You continue to play the game. Okay. Pick 2 people and go. So they started here. Immediately they got pulled right down to there. So, okay, you guys can all sit down. So the other one, in the coward, exploded. But this one, what did you see? You saw him collapse. Well, you saw something else. Well, when you collapsed, well, there was still movement. Can you kind of recall what that movement was like?
Circling.
Do this motion. What does that mean? Circular. So they kind of, not only they collapsed, but they kind of spiraled around. Okay. Now those have taken differential equations and might be taking a phase portrait already. Okay. And you should. If I'm going to write down a mathematical model of this particular situation, I'm going to make a conjecture that for any initial condition, that the system should collapse down to a single point. I should see some rotation. I should be able to prove that mathematically if I have the right type of model. Okay. Now, and I'll look at some other simulations if I go back over in here. Oops, let me go. No, I want to go back and use one. Go here. And just to look at pictures of that. So, okay. And so this, again, this is an initial condition. There's 1,000 agents there, believe it or not. Just a lot of them are off the screen. Okay. And they just eventually all kind of undo the explosion. Okay. End up in a single concentrated point. Now you can't really see the spiraling motion around, the movement around, but you definitely see it collapsing down on a single point. Okay. So 3 different types of rules. One, I just follow a particular agent. I keep a minimum distance, and you see it just kind of circle around. You have some sort of periodic orbits, and they eventually collapse down. But takes actually a long time for it to collapse down to a single point and come to static. Okay. It's telling me that I have meetings at SFA. Hopefully no one will say, like, where are you? Second one, so you have one just nice circular orbits, and they eventually collapse down to a static equilibrium. You have another one where they explode away. You have another one where they really rapidly come down to a cluster and then have some rotation. But these are just simple examples of simple rules that I can get emerging behavior that comes out of that. And these are just the simplest ICO systems that I could write down the equations of motions for. Okay, so we're going to walk through how we might model this using our tools of mathematics. Okay, so let me kind of get through here. Okay, so these are kind of our 3 situations just in a picture. So the peacemaker, you went right into that red dot. If you chose agent J and agent K, okay, you go right into the middle. If I was a coward, I chose agent J and agent K, and I try to get agent K to be in the middle. If I'm the follower, I'm just going towards agent J. Okay, and this is kind of a picture. And if I'm looking at just an XY plane here, each one of these P's has 2 components. It has an X component and a Y component. And I want to know how those X components and Y components change with time. And what I'm showing in the picture here is how the velocity would change, okay, in a current configuration. You would look right now at the current configuration, you would choose a direction you're going to move, okay, and you would take a step in that direction. Another second goes by, all the storms have also made an adjustment. You would then look at the situation again, and you would adjust your velocity vector's direction, okay? And if you maintain that constant velocity and maintain how big of a step you can take over a second, okay? So, who's had Calc 1? Okay. Who's en route to take Calc 1? Okay. Now, if you've in Calc 1 or taken Calc 1, you may or may not have run across vectors. Okay. Who has never heard of a vector? Ah, cool. Okay. That's really surprising. Either that or you're just too bashful you don't want to admit it. Okay. I never heard of a vector at all until I got to Calc 3. Okay. So I remember being my first year at school, and they started off and they said, I have this vector and you had to apply in 3D, and I was like, what the heck is this thing? I thought it was way over my head. And so, and till this day, when I teach Calculus 3, I often tell students at some point in this class you're going to feel like the rug got pulled out from underneath you. For me, it was day 1. I was like, wow, I think I'm in trouble. But I'm going to walk you through how we can use vectors here to write down our systems equations that would model all 3 systems. And we're going to get from that actually a more general model, that this one model will actually be a general model for all of them. Okay, so we're going to go. So a little vector primer. This is why some of you have graph paper to kind of play with this. So I want to make sure that you know how to use vectors appropriately from a geometric perspective. Okay, and those are the well experienced with vectors. Okay, you want to get the fundamentals as deeply known as possible. I'll give you an example. I can take who plays the piano here. Okay, so all of you that play piano probably can play Jingle Bells. My first grader, she can play Jingle Bells now. Okay, but when I compare that to how you play Jingle Bells, it's still a very simplistic song. It'll be so much better than the way my daughter Adeline will play Jingle Bells. Even if the person who is more masterful, even will go back to the foundations and play with such succinct power to it. It's beautiful how they can play just Mary Had a Little Lamb. You take a classic pianist and you have them play the most simplest piece, it'll dwarf whatever skill you think you may have. It's like, oh my goodness. So same thing goes on. You may think you're real experienced with vectors. We're going to get a little bit of overview of how to use them. Okay, so I want to get a vector that goes from A to B. So all vectors have two parts. Okay, I'm vector. Okay, I am something that has source and magnitude. I have direction and magnitude. Okay, from Despicables. Okay, I'm vector. So, but that's a very physical way of thinking about a vector, like wind velocity or speed of my car. I'm going 60 miles an hour northwest. You give me the direction and the speed. Okay, but I also want to look at vectors as displacements. How much I've gone from A to B. So if you were to encapsulate a vector, it's a directed line segment. I'm going from A to B. You're going to use this mathematical object to store how much you've changed in your x components and your y components. How much has the x component change of gone from A to B? 2. And how much has it gone from going from A to B in the y coordinates? Is it 6, 5, what is it? 1, 2, 3, 4, 5, 6. Okay. So I have the vector. What's the vector then? So 2I plus 6j. Okay. Now, of course, you could find the angle. You know, you'd use trigonometry here. Okay. And also you can get the length, the magnitude, by using Pythagorean theorem. Okay. But remember, there's two ways of looking at vectors. One is a very pragmatic and physical view of vectors. They have force and magnitude. The other is looking at them as they store displacements. You go from here to there. And you can go back to your velocity idea. If I'm going 60 miles an hour northwest, you absolutely have a prediction of how much my position is going to change if I travel for a second. So I'm going 60 miles an hour northwest. So you can look at vectors in those two different ways. Okay. So just storing that, I have that vector 2, 6. Okay. So think about in terms of the storms. What I want to have, I'm going to store the current position of an agent at this location, and I'm telling how much this position is going to change by looking at another agent's location or agent's location. Okay, so kind of go in through there. Hey, the vector 2, 6. Did that matter if I had an origin here or here or here? Would it always be the vector 2, 6? And that's kind of the beauty of vectors. There's someone right now in this country going 60 miles an hour northbound. Okay? I was doing that maybe like an hour and a half ago. Okay? There are many places on this earth that the current wind velocity is due west at 15 miles an hour. Okay? So, but that's kind of cool. But you can start thinking about adding and subtracting vectors by using origins. So look at your picture that you have. So I have this picture. Okay, so if you don't have this, sorry. I only printed out, I can't remember, the whole amount of this room minus the number they're given out. So I have this picture. Okay. So if you don't have that picture in front of you, look at someone else's. But can you give me the vector that goes from the origin to point B? And I'll make that origin be the bottom left-hand corner. What do I have? What do you have? So 2I plus 4j. Okay. All right, good. I want you to give it kind of, we're just going to test your kind of your background of vectors here. Okay. What about the vector that goes from the origin to point A? What do you got there? Okay. Can you get a vector that goes from the point A or point B to point A? Okay, so you can look at those as well. But you also could get that by using our parallelogram rule and subtracting our vectors, and you can get the same thing. And let me put that together with how I can do this with our situation. So I got an agent A and agent A wants to go toward agent B. Okay, I want to create that vector. You can think of, I want to, whatever the location of A is, I'm going to go back to the origin. So I'm going to travel from A to here. Okay, and then I just travel up to the B vector. So if I want to look at the change of agent A's location, or what its velocity vector is, okay, if I put it in terms of an arrow, I want it to go by some amount in the direction of B minus A. Okay, that would be the velocity vector. Okay, and you can think about another situation. If I have agent A, and this is the peacemaker, what does it want to do? Go right in between. Okay, so it wants to go right in between. How do I construct that vector? Well, one way to do it is go back home. What vector would that be? Negative 5, 1. I'm going to write that as minus A. Minus A. It gets me back home. And then let's go to B. So plus B. And then how do I get a vector that goes from B to C? So you can think of C minus B. Okay, or half of C minus B. Okay. And so I can play with that, and that's what I have written there. Minus A is you go back home. Plus B gets me to the point B. And then C minus B is a vector that goes from B to C, and I want to go half of that. And of course, we can simplify that a little bit. But that's what that velocity vector is. Okay? So let me put this kind of all together. All three of them. Okay? They didn't give you the coward, but... so I'm writing down in terms of the change, or I say the velocity of p sub I, agent I for the follower. If I'm going to, minus pi says go back home, and then go toward the pj position. Okay. The gamma is at what rate it goes. Okay. The peacemaker, if I have pi, the minus pi says go back home, and then when I simplify, it goes to the average location, pj plus pk over 2. Okay. Same thing here. If I want to go have agent k be the middleman, I'm going to go back to pi, or back to the origin, and go to that location just by playing with those vectors. See, but now I have a dynamical system.
We have about 2 minutes.
Okay.
Want to summarize or get any questions?
I will. So now I got a dynamical system. Every single one of those models follows that first order differential equation. And how many differential equations do I have there? How many? How many do you have? Okay, so I just have for agent I there, it's for every single agent. So I have a system of linear differential equations. And if I have 1,000 agents, I have 1,000 of them. But I actually have twice that, because this is that vector p sub I has two components, an x component and a y component. Okay, so for if you have 1,000 agents, there's actually 2,000 linear differential equations there. But what's beautiful about it is you can start writing that down in terms of a matrix. And you can start looking at the matrix properties. And those are that have been fortunate enough to get into linear algebra, you start learning about these eigenvalues and eigenvectors. And they completely dictate the behavior of the mathematical model, the long-term dynamics. And we can do that for all three of these ecosystems. Okay, which is kind of neat. Okay, so let me get to my last slide here. I'm going to get over and skip through. This goes through all of that. Now look at the dynamics and the exact. I'm going to skip through this.
Man, you know, good stuff.
I know, there's lots of good stuff. But here's some conclusions that you can get by doing this linear algebra analysis. Okay, literally doing a combination of your linear algebra background and your differential equations, which some of you may not be in yet. Okay, you can find out that the follower, for any initial condition, it collapses down to a static equilibrium and it rotates. But you can find that it doesn't rotate nearly as fast as the coward. Or sorry, the peacemaker. Okay, and you can find out that the coward just explodes by looking at that. So you can actually now get a mathematical proof for these rules. I have a direct correlation between the model and actually the system, and to be able to show the behavior. To this day, This is the only such mathematical proof for any swarm model out there. And this was in 2007 by Ian Gravani and Robert Marks, the IEEE paper. Okay. I thank you for your time. I know you have to get to class. And I'm sorry about the videos didn't work. I hope you at least go to that site and look at them later on.
All right, let's talk about We'll answer them. Otherwise, we'll see you for lunch.
No, it's not.
What's up? No problem. Oh, thanks.
I never got the sign-up sheet.
Okay, hang on a second.